Welcome to Applied Math. This is part 2 of lecture 2. We're going to look at prime factors and common multiples. Okay, so to explain prime factors, let's start by talking about what are numbers built with. So for example, if I say, hey, the number 10, what is that built with? Well, one way of thinking of it is 10 is equal to 6 plus 4. But then we could keep going and say that that's just the same as, I don't know, 3 plus 3 plus 2 plus 2, and then we could keep going. And eventually we'll just get down to 1 plus 1 plus dot 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 plus 1 10 times. Right, and that's boring. So what we're doing here is looking in a purely additive sense. So looking just at addition and how do we build a number with addition. And that's boring because every single number that you pick is going to break down to just however many ones, right? So rather than looking at addition, let's look at multiplication. How do we build a number from multiplication? Well, 10, we can break it into what are called factors. Okay, so for example, the factors of 10, well, one way of factoring 10 would be 1 times 10. So what we've got here is 1 is a factor of 10 and 10 is a factor of 10. But that's, once again, the boring answer, right? Those are obvious. For any number that you pick, 1 will be a factor of it, and the number itself will be a factor. So instead, let's look at another option, which in this case would be 2 times 5. Okay, so this is a new way of looking at it, right? We have 2 times 5 equals 10, that's true. So 2 is a factor of 10, and 5 is a factor of 10. So let me just write down a quick definition of what a factor is. A factor, so definition, we can say that P is a factor of some whole number let's call it n, just so that we have something to represent that whole number. So P is a factor of a whole number n if there is some other number q such that P times Q is equal to N. So notice actually that if you have one factor P and then you've got some other number Q, Q will also end up being a factor because we could just swap the letters P and Q around and the definition will still be true for Q. Okay, so looking back to 10, 1 is a factor of 10, 10 is a factor of 10, because 1 times 10 is 10, 2 is a factor of 10, and 5 is a factor of 10, because 2 times 5 is 10. Okay, so a few other examples. 9 has factors. We could represent 9 as 1 times 9, which is the boring way, but we could also represent it as 3 times 3. Okay, and 3 is a factor of 9. Notice in this case, the P and the Q happen to be the same number, and that's okay. Okay, so these are the factors of 9. Now, the question is, can I go any further? Looking back here at 10, I had it equal to 2 times 5. Can I break this down? Well, I could break it down to say, well, 2 could be broken down into 1 times 2 times 5, let's say. So then, now I've got this times 1. I could put, well, 1 could be written as 1 times 1, which could be written as 1 times 1, could be rewritten as 1 times, right? We could break it down over and over and over again with just a bunch of 1s, and that would, once again, be boring. So we're going to basically at this point we can pretty much ignore 1 as a factor because it's always there. It's just always sort of hidden. So we don't need to think about that. So what we've got here, we seem to have run into this sort of dead end that we can't go any further, right? Unlike with addition, where you can always just break things down into ones, right? So with 9 as well, right? We factored it and we got to 3 times 3. Can we break 3 down anymore? It doesn't seem like we can. So that gives me a new idea of a type of number, which we will call prime numbers. So what is a prime number? So a prime number is a number that has factors, but the only factors that it has, only factors, are 1 and itself. That's what a prime number is. Okay, so let's take a look. So we have, first off, I should make one thing clear. Not 1, okay? 1 is not a prime number. Why? Well, because 1 is weird, all right? 1 is like 0 in adding, right? In adding, I could also break this down if I wanted to by saying, oh, it's 10 ones and then a million zeros added together, right? And that's not interesting. Same here with multiplying. I could say, oh, and I'm multiplying by, a gazillion ones. It doesn't change our answer, so it's not worth looking into. So 1 is not considered a prime number, okay? It is true that by this definition, without me stating it's not 1, that 1 would fit that, so I need to make a very specific exclusion here, saying not 1. All right, so that's prime numbers. So let's take a list here. 2 is a prime number. It's the first prime number. It's also the only even prime number. And if you think about it for a bit about what even means, it'll be very clear why it can be the only even prime number. Okay, so there's a little bit of a mind bender for you. Hopefully your mind isn't too bent. All right, 3 is the next prime. 4 isn't prime, right? Because 2 goes into 4. So the next number is 5, and 5 is prime. 6, no, because it's 2 times 3. 7 is prime. 8 isn't, because it's 2 times 4. 9 isn't, because it's 3 times 3. 10 isn't, because it's 2 times 5. So the next one is 11, and we could keep going, right? 13, but not 15. I'm just skipping the even numbers at this point because I know that they're not prime. 16, no. 17, yes. 19, yes. 21, no. So then the 23 would be yes, though, right? So, okay, we can keep going with that. So these numbers are what all the other numbers are built out of, except for 1. Okay, 1's its own thing. Okay, but these numbers, every other type of number, which are called composite, so the composite numbers, those are the numbers that have more factors than prime numbers. So composite numbers has let's try that again. Has more than just 2 factors. So in other words, 3 or more factors, okay? And every composite number is built out of prime numbers in some way, and we'll take a look at what I mean by that in just a moment. So every composite number has more than just 2 factors, or has 3 or more factors, right? And so that's why they're called composite numbers, because they are composed of the numbers that do have only the 2 factors, 1 in itself. Okay, cool. Now on to talking about prime factors, and then we'll take a deep dive into what composite numbers are to talk about prime factors. Okay, so let's talk about prime factors. So every composite number has prime factors, and so let's pick a composite number, 126. I know that this is a composite number because, for one, it's even, and every even number other than 2 is definitely composite. It can't be prime. Why? Well, because if it's an even number, then that means it's divisible by 2. What does divisible mean? It's the same thing as saying it has a factor of 2. So 2 goes into this, so 2 is a factor of it. Therefore, this is a composite number. So what I want to do now is explore what do I mean by saying that every composite number can be broken down into its prime factors. So what we're going to first do is say, well, how can I write this as a pair of factors? Well, I've already said that 2 goes into this number, so 2 times what is 126? Well, so I'm going to write sort of this tree diagram is the idea. 2 is prime, so I'm going to circle it, and then 2 times what is 126? Well, let's see. 6 divided by 2 is 3, 12 divided by 2 is 6, so this is 120, that's 12 tens, dividing that by 2 is 60, right? And the 6 divided by 2 is 3, so this gives me 63. Now, is that prime or is that composite? Well, looking at this number, 3 can go evenly into it. And how do I know that? Well, I know that 3 goes evenly into 60, and so it also goes evenly into 3 as well. And when I add 60 plus 3, it's got to go into that. So there's that. So 3 goes into 63, so I can take out a factor of 3. And now 60 divided by 3, or 6, just think of 6 divided by 3, that's 2, so 60 divided by 3 is going to be 20, and then 3 divided by 3 is of course 1, so that gives me 21. Okay, now there's a hidden rule, by the way, about divisibility by 3. If you have a number and you add up the digits of that number, and you get a multiple of 3, then the original number was a multiple of 3. Okay? And if you're not sure if the number you get is a multiple of 3, add the digits of the number you get. So let's just pointing out it works up here because 1 plus 2 is 3 plus 6 is 9, so 9 is a multiple of 3. So therefore this works. 3 will go into this number. 63, add those together, you get 9, and so 3 will definitely go into 63. Add 2 and 1, and we get 3, so 3 also goes into 21. So I know that 3 is a factor of 21. Now, what is 21 divided by 3? Well, let's think about this. Okay, hopefully you already know the answer to this because you've practiced your multiplication tables from the last lecture, and you should get that it's 7. Just in case you didn't though, let's say what is 21 minus, let's say, how about 6? 21 minus 6 is 15. So rearranging this, 15 plus 6 is equal to 21. So now we can write this as factors of 3, right? I know that this one becomes easy. 5 times 3 is 15, plus 2 times 3 is 21. So that means, rearranging, 7 times 3 is 21, right? If you need to have some ways of doing this, this is a way you can do it in your mind. You wouldn't necessarily want to write this out to figure out how to do this division, but if you wanted to find a way of doing this short division in your head, you could think, hey, well, 21, if I subtract 6 away from that, I get 15. I know that's 5 times 3, and I know that 6 is just 2 times 3, so 5 plus 2 is 7, and I'm done. Okay, that's one way of doing it. All right. Cool. Otherwise, hopefully you just have it memorized at this point. The multiplication table, 3 times 7 is 21. All right, it's an important thing to remember. Okay, cool. So what have I got here? I've now said that 126 is equal to 2 times 63. And then I said that 63 is 3 times 21, so I can rewrite this as 2 times, rather than 63, I can write this as 3 times 21. But once again, I said that 21 is equal to 3 times 7, so this is 2 times 3 times 3 times 7. Okay, so what I've done there, and what you can do when you're writing on a test, you can just jump straight to saying, oh, I know what all my prime factors are. 126 is 2 times 3 times 3 times 7. Or if you want to shorten that, you could recognize, oh, there's 2 3's, so it's 2 times 3 squared, right? Because 3 times 3 is 3 squared, and then times 7. And put a box around it to say, hey, that's the answer. Right, so those are the prime factors of 126. Okay, cool. So that's how we prime factor a number. Let's try one more example. All right, let's take a look at a new number here. 175. Now, I know that this number is composite because I know that if a number ends in a 5, then 5 itself will be a factor of that number. Okay, I know that 2 doesn't go into this number because it's not even. And I know that 3 doesn't go into this number because if I add up the digits, so 1 plus 7 is 8, plus 5 is 13. 3 doesn't go into 13. And I can check that real quick because 1 plus 3 is 4, which is not a multiple of 3. So therefore, this is not a multiple of 3. Therefore, 2 and 3 are out as possible prime factors. So 5 is my first choice. So this number is going to be 5 times some number. Okay, so let's break this down. 175, I could think of that as just 175, and I can now think of, okay, what is 100 divided by 5? Right, so dividing 100 by 5 is 20, right? Because it's like dividing 10 by 5 and putting the extra 0. All right, what about 75? Well, 70 divided by 5 is 14 because you would, because to divide by 5 is the same as dividing by 7 and then multiplying by 2, right? So there's a quick way of doing it. So 75 is going to be 15. So dividing by 5, and then adding those together gets us 35. Okay, is 35 prime? No, because it ends in a 5 and it isn't 5 itself. So we can then factor out another 5. Okay, 35 divided by 5. This one's a little easier. Okay, you can, to divide by 5, the easiest way is to divide by 10 and then multiply by 2. Okay, dividing by 10 gets us to 3.5. Multiplying by 2, 3.5 plus 3.5 is 6, and then 0.5 plus 0.5 is 1, so that is 7. 7. And 7 is a prime number, so I can circle that. And so 175 is equal to 5 times 7. Or, put it more succinctly, 5 squared times 7. So that is my answer. That's my prime factorization of 175. Okay, cool. So the next thing that we need to talk about is common multiples. Okay, so we'll start a new page and talk about that. Here we go. Okay, so we're going to talk about common multiples. Before we get too far ahead, though, I suppose I should define what a multiple is. Okay, so a multiple. So a multiple, let's say, call the number n. n is a multiple of some other number p if p is a factor of n. So if p is a factor of n, then we can just turn it around and say, well, n is a multiple of p. So for example, I know that 2 is a factor of 10. So that's the same thing as saying 10 is a multiple of 2. Okay? Saying the same thing. So multiples, factors, they're saying sort of the same concept just from the opposite sides, right? So the bigger number generally is the multiple, the smaller number is the factor, is what we say. So the number that goes into the number is the factor, the number that is being gone into. Yeah, the bigger number, the product, is called the multiple. Okay, so a common multiple comes out of common multiple. So common multiple, in order to talk about common multiples, we need to have two numbers for this to be a common multiple of. Okay, so this is they would share this multiple in common. So a common multiple, so n is a common multiple of, let's say, p and q if both p and q are factors of n. Or put another way, or we could just say if n is a multiple of p and n is a multiple of q. So if you have both, it's a multiple of both p and q, then it is a common multiple. Okay, now hopefully you understand why it's called that. All right, great. So let's take a look at two numbers that may seem a little familiar. Here we go. We've got 126 and 175. So one way of finding a common multiple would be to just list all the possible numbers. Now that can take a while, but well, I've got the power to fast forward, so to shrink time. So let's try that real quick. So I can just multiply this by 2 to get, hold on, I'm going to get my calculator out. And I know that you guys aren't allowed calculators, but this is just going to make things faster for the point of view of watching. So multiplying by 2 is 256, adding another 126 gets us 378, plus 126 is 504, plus 126 is 630, plus 126 is 756, plus 126 is 882. Okay, this is taking a while. Plus 126, 1008, plus 126 is 1134. So 1134 plus 126 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 Okay, and now for 175, we're going to find the multiples of that. So 175 plus 175 is equal to 350 plus 175, 525 plus 175, 700 plus 175 is 875 plus 175 is 1050 plus 175 is 1225 plus 175 is 1400 plus 175 is 1575 plus 175 is 1750. Any of these matching yet? Nope. Plus 175 is 1925 plus 175 is 2100 plus 175 75 plus 175, 2,450 plus 175 is 2,625 plus 175 is 2,800 plus 175 is 2,975 plus 175 is 3,150. There we go. We've got it. We found the common multiple. So what I've done here is I've just listed multiples of 126 and listed multiples of 175, and I have found a common multiple of 126 and 175. This is the least common multiple. It's the smallest number that both 126 and 175 goes into. There's gotta be a better way. All right, so what is the better way? Okay, so what we need to do is look at what these numbers are built out of, okay? And then build a new number using just what we need to make sure that the new number we have has everything to build 126 and everything to build 175. Okay, so let's start by writing out just the numbers the prime factorization of 126, because we know that at least there will have to be a 2, 2 3s, and a 7 in our new number, okay, to build our new number. Then, once you have that, we can then look at 175 and say, okay, what do we need to add to this so that 175 can also be built with these numbers? Well, we don't have any 5s, so I need to multiply in those 5s as well, but I already have that 7, so I don't need to go any further than that. So this is the least common multiple of 126 and 175. Least meaning smallest. It's just the tiniest of the possible multiples. And it's not very tiny, as you remember from just a moment ago. So if I were to multiply this up, well, let's make it a little bit easier on ourselves. Let's see, 2 times 5, that's 10. 3 times 3 is 9. 7 times 5 is 35. Okay, 9 times 10 is 90 times 35. Okay, this I can do real quick. 35 times 90, 0 times 5 is 0, 0 times 3 is 0, so we don't have to worry about that. We can just skip ahead, put a 0 down and say, okay, 9 times 5, well, that's 45, and 9 times 3, that is 27, right? And then adding 4 to that gives me 31. And lo and behold, 3,150, which is the number that we got before. Okay, so that's much faster, okay? Even without a calculator, doing a bunch of multiplication here is much faster than doing all of this addition, okay? Okay, so that's the way of finding the least common multiple. Now, if you wanted to just find any common multiple, the easiest thing to do might be to just take 126 and 175 and multiply them together. But what will happen then is you'll get numbers that are a little on the big side. 126 times 175 times 175 ends up being 22,050, which is a little bit bigger than maybe we want to work with. So what I'm showing you here, this is a method that you can use to find the least common multiple, which can be helpful when you're doing work with fractions. Remember fractions? That's the whole point of this lecture. So we're going to get back to fractions in a moment now. But yeah, that is common multiples. If you can find common multiples of any sort, then we can do work with fractions using those common multiples. Finding the least common multiple, like we did here, is just a way of making the math turn out to be the easiest, okay, for you. So we don't have to handle huge numbers. Okay, excellent. So now on to talking about how do we do actual operations with fractions.